So where we left off today in class was talking about how not every intermolecular force is the same, but how they have varying strengths. So for example, if we'd had more time, we could have predicted, whoa, which one do you think is the weakest, or which do you think is the strongest? And what we would have found is that the weakest are the London dispersion forces, then the dipole-dipole forces, with the strongest being hydrogen bonding. Now what we're going to see is that the amount of intermolecular forces that molecules have will determine some of their properties. So let's just talk about boiling point and melting point, and for the purposes of this class you all can just omit freezing point and not have to worry about it. So in boiling, we're going from a liquid to a gas state. So if we kind of think back to the early chapters of this book and we're contrasting liquid versus gas, which one might you predict would have the least interactions between its molecules? Alright, so you'd probably predict that a gas, because in a gas state of matter, the particles are kind of far apart, they're moving really fast, so they would interact less than they would in a liquid, where the particles are still close together, they can just kind of slide past each other. And so, if the gas state has less intermolecular forces than the liquid state, then we can kind of predict that, okay, well, if we have these molecules and they have low intermolecular forces, then it's going to be pretty easy to go ahead and put them into the gas state. However, if it has high intermolecular forces where those molecules are really kind of attracted to each other, it's going to be very hard to break them apart and get them into the gas phase. So what we see is that the higher the amount of intermolecular forces, then the higher the boiling point. Okay, higher the boiling point. So let's take, for example, why CCl4, carbon tetrachloride, boils at a lower temperature than water. So if we look at carbon tetrachloride versus water, what we have to do is consider which intermolecular forces are present. So between molecules of carbon tetrachloride, what we see is that although this molecule has polar bonds, if we consider the directions of all these dipole moments, it will spread electron density evenly across the molecule. So this will be a non-polar molecule. Okay. So that means, since it's a non-polar molecule, we're not going to see any dipole-dipole forces, nor will we see hydrogen bonding, because there's no hydrogen attached to an electronegative atom. However, all molecules do have London dispersion forces, so those will be present in carbon tetrachloride. Now water, on the other hand, is a polar molecule, so it will have dipole-dipole forces, and it also has hydrogen bonded to an electronegative atom, so hydrogen bonding will also be present. And of course, like everything else with an electron cloud, it will also have London dispersion forces. So the way that's easiest to go about these problems is to consider your molecule and then list out the types of intermolecular forces that will be present. So now that we've done that for each molecule, let's compare and see which ones have greater intermolecular forces. So here water has dipole-dipole, hydrogen bonding, and London dispersion forces. So its molecules will be much more strongly attracted to each other than molecules of carbon tetrachloride. So because its molecules are much more strongly attracted, it's going to be much harder to break them apart. So we're going to have a higher boiling point so we can supply more energy. And so that's why water does have such a high boiling point of 100 degrees Celsius. Okay, so again, the greater the amount of intermolecular forces, the higher the boiling point. Now let's talk about melting point. So in melting, we're going from a solid to a liquid. And again, a liquid state, there are less interactions, in a liquid state, the molecules are, less tightly bound than they are in the solid state. So again, there will kind of be less attractions between molecules in the liquid state. So kind of as a result of this, what we'll see is that the greater the intermolecular forces, the higher the melting point. So that means since the molecules are already very attracted to each other, we're going to have to supply more energy to break them apart and melt them. So let's consider here our examples between CH4 and C3H8. So here they're both nonpolar molecules, so we know they're both going to have London dispersion forces due to those interactions between temporary dipoles. But now we have to consider, okay, well, which one will have more London dispersion forces? So again, if we think back, we know that C3H8 has a bigger mass, so it's going to have a larger electron cloud. So it's going to be able to participate in more of those interactions. So, as a result, it'll have a higher amount of London dispersion forces than just CH4. So since C3H8 has the higher amount of IMFs, then it will also have a higher melting point. Sorry, the lights just went off. Okay, and the last thing we now need to talk about is about solubility. So basically the rule to remember is that like dissolves like. And so how we kind of translate this is that whenever we're trying to dissolve a polar molecule, we have to pick a polar solvent to dissolve it in. And likewise, whenever we're trying to dissolve, dissolving just means to put it in solution, a nonpolar molecule, then that means we have to put it in a nonpolar solvent. Okay? So take, for example, if we have CH3OH, that will look like this, and then C2H6. So if we first take time to classify these molecules, because of this oxygen here, the electron density will be pulled this way, so this will be a polar molecule. But however, this one will be a nonpolar molecule. Electrons are distributed evenly. Okay, so that means that now we have to pick the best solvent to dissolve these in. So if our solvent is water, now our question kind of is, well, okay, which one of these will dissolve in water? Well, we first have to ask ourselves, okay, is water polar or nonpolar? And as we've already kind of discussed in class, water is a polar molecule. So that means we would know that CH3OH would dissolve in water, while C2H6 would not. Okay? And this explains things like why oil will not dissolve in water. For example, oil is nonpolar and water is polar, so they're unlike, so they don't dissolve. So again, like dissolves like, so you must pick a polar solvent to dissolve a polar molecule. But for this nonpolar molecule, we would have to pick some other nonpolar solvent. All right, hope this was helpful.